Today we're talking about energy conservation. So we're going to start out here with just a kind of simple up and down motion. So this is just the same ball doing this parabola at different points. So it's going to start with this initial velocity and then it's going to follow this path. And then here we have it at its peak. And then here we have it when it came back down. So I want to talk a little bit about what happens during this entire process, looking at work done specifically. So I'm going to show you the direction of the displacement and the direction of the force for these kind of three different timestamps. And D is for displacement, F is for force. So starting out, we have an initial velocity and we are going up. So the displacement is pointing up because that's what direction the object's moving, but the force we're looking at here is the weight force or the gravitational force. So that always points down. So that means that the displacement is pointing up here, but the force is pointing down. And with work being the force times the displacement times cosine of the angle, that tells us that the work here to get from the bottom to the top is negative mgy. And remember, this comes from mg is the force here because it's just the force of gravity or the weight. And then y is the change in position here. So the work done to go from the ground to the peak is negative mgy. At the peak, there is no displacement because it's temporarily stopped for a second, but the force is still pointing down the whole time. And then it's going to travel down. So the displacement will be down and the force is down. The force is still the same. It's still mass times gravity. And now our displacement, we're still traveling a distance y, but this time the displacement and the force are in the same direction. So we end up with the work done to go from the peak back to the ground of positive mgy. Now, the net work done in this situation is for like this entire trip, if you will, of the ball, is the sum of the work done for the different parts. So the net work is this work plus this work. Well, that's 0. So the net work done in this situation is 0. So our object starts on the ground, goes all the way up, and comes back down to the ground, and no work is done. And I want to look at this in another way too, and then we'll get into why this matters. So, another thing that's important to think about with forces with respect to energy is whether or not the work done depends on the path taken to go from point A to point B. So let's say you're bringing a box to the first floor from the basement. So here's the box, mass M, and we go from the first floor from the basement to the first floor is height h. And just like on the previous slide here, the weight force is pointing down, or gravity is pointing down, and the motion is up. So those are in opposite directions. That means the work done is negative. So to go from the basement to the first floor for trip A, it's negative mgh. Now we can look at a different path. What if instead of going straight to the first floor, we go up to the second floor and then down to the first floor? What does that do for the work done? So going from the basement to the second floor, it's just twice the height. So we just end up with negative 2 mgh. And then we want to go from the second floor down to the first floor. So in that case, the motion and the force are in the same direction. So we have positive work. So we get positive mgh. And if we combine these for the total work done in the situation, we get negative mgh, which is the same as this direct path that we took instead of taking this kind of extra windy path, excuse me. So the point of looking at this is in part that forces that do this, where if the endpoints are the same, no matter how you get from point A to point B, as long as those endpoints A and B are the same, the work done to get from one to the other is the same, even if you go up to the second floor first and then back down. And this is a conservative force when it works this way. Or like on the previous slide, what we saw was an object traveling, doing some sort of motion. It just like went up and then came back down, but its initial and ending points were the same. So the work done was 0 because it might as well not have moved, at least for what the work done cares anyway. So we can represent this another way too. So we have a hiker and there's 2 options for paths they could take to get to the summit. So they could do path A, that's more like less steep, or they could do the super like steep, pretty much rock climbing path B. And either way they do it, the work done to get to the peak and also the change in gravitational potential energy is the same, because the starting point and the ending point are the same. So it doesn't matter if they take the more gradual path or if they take the super steep path. And this doesn't matter because gravitational force is a conservative force. So it allows us to not be worried about the path taken and instead just about what the endpoints are. And not all forces are conservative forces. For example, I'm not going to go into the detail, but friction is not a conservative force. So if we were looking at the work done by friction, it would matter what path we were taking to go from A to B. Okay, now with that, I want to look at how the potential energy here in our original situation relates to the kinetic energy. So we have this energy graph. Potential energy is green and kinetic is blue. And this means 0. I didn't want it to disappear all the way, but that's 0. So we're starting here just looking at the initial position. So initially we're at a height of 0. So the gravitational potential energy is 0. But then we have an initial velocity. So what we end up with is our maximum kinetic energy and our minimum potential energy. But then let's look at when we get to the top. At this point, we know that for a second there, the velocity is 0. So the kinetic energy is 0. And this is also the peak height, the highest this ball is going in this trajectory. So that means it's the maximum potential energy. And then again, when we're back on the ground, the same thing as where we started. The potential energy is at its lowest and the kinetic energy is at its highest because these are the maximum values of the velocity. And this sort of relationship of the bar graphs, you can also see all throughout the motion. So if we looked more kind of halfway up, we would see an even split. The bars would be the same size because kinetic energy would have decreased because velocity was decreasing, and potential energy would have increased because the height was increasing. But sorry, I don't have those parts of the graph. Okay, so what's happening here, or what this is evidence of, is conservation of energy. So in an isolated system where only conservative forces are acting, isolated means that there aren't external forces that we have to worry about. And then conservative forces like the gravitational force are acting, the total mechanical energy remains constant. Mechanical energy is the sum of energies that we've learned about so far, like that we've worked with so far. So mechanical energy is the kinetic plus the potential. Okay, and so is this saying in an isolated system with only conservative forces acting, the total mechanical energy remains constant. So this E is equal, the initial energy is equal to the final energy. And since this mechanical energy equals the kinetic plus the potential, we also get this relationship where the initial kinetic and initial potential equal the final kinetic plus the final potential. And I will show you why this is useful and important with this next example. I'm going to talk you through it and then we'll move to work on it. So the summit plummet is an extreme water slide, one of the steepest and fastest in the world. Riders drop 36 meters from the start until they hit a run out at the bottom. If you give yourself a good push at the start so that you begin your plunge moving at 2 meters per second, how fast are you moving when you get to the bottom? And then it also asks how fast you would be moving if you skipped the push. So if your initial velocity was 0. And since the slide is steep and slippery, we can assume that we can ignore friction and drag forces. Okay, so let's start kind of the classic way that we learned with our knowns. And we're just we're gonna start with this situation where you give yourself a push to get going so you have an initial velocity, and then we'll just do it over with the other one. So our initial velocity is 2 meters per second. The initial position in y is 36 meters. The final position in y is 0 meters. And unknowns, or at least what we want to find, is the final velocity. So the slides before this problem were on conservation of energy. So let's go over that. Energy, initial energy equals final energy, and then the energy equals the kinetic plus the potential. So this is telling us that initially the kinetic plus the potential is equal to the final kinetic plus the final potential. And then let's remember what the equations are. So kinetic is 1/2 mv squared, and potential, gravitational potential anyway, is mgy. So let's write this, kind of expand this equation out. So we have 1/2 mass initial velocity squared plus mass times acceleration due to gravity times the initial y. And that equals 1/2 mass final velocity squared plus mass gravity times the final position. So one thing we can do now is get rid of some stuff. So the final position is 0. So this whole final gravitational potential energy term is 0. And then all 3 of the rest of the terms, and actually all 4 before we canceled that out, have the mass in them. So we can cancel that out, which is good because we didn't know the mass. So glad we can solve the problem still. 1/2 v initial squared plus gy initial equals 1/2 v final squared. And then we just want to solve for v final. So that's going to look like multiplying both sides by 2 and square rooting them. So we get the square root of 2 times 1/2 v initial squared plus g times y initial equals the final velocity. And we can plug in our numbers now. 2 times 1/2, 2 meters per second, whole thing squared, plus 9.8 meters per second squared times 36 meters. And this gives us a final velocity of 26 point, I think it's 64. Yeah. 0.64 meters per second. Now, so that was the situation when we start with a push. We start with that initial velocity. Also, that's really fast going down a water slide. That seems dangerous. Anyway, so, and again, what we did is we just set those energies, the initial mechanical energy equal to the final mechanical energy, rearranged it to solve for the final velocity. So now let's just look at the situation where V initial equals 0 instead. So we're going to start from, actually from the equation below that, sorry, from this equation before we canceled anything out. And then we'll do some canceling. So here's our initial kinetic energy is 1/2 mv squared, initial squared. Initial potential energy is mgy initial. And then final kinetic energy is 1/2 mv final squared plus mgy final. Okay, now, I'm trying to pick a color. Okay, so actually I'll use this. The initial velocity here now is 0. So that term goes away. And just like before, the final height is 0. So that term also goes away. So we're just left with these two terms and they both have mass. So that goes away again. So we have G times Y initial equals 1/2 V final squared. And we can solve for V final the same way as before. So we multiply both sides by 2 and take the square root of both sides. So we get the square root of 2G times Y initial is equal to the final velocity. Square root of 2 times 9.8 meters per second squared times 36 meters. And this one gives us a V final of 26.56 meters per second. So you might have been wondering why I didn't round more. This is why I wanted to show that they're not identical, but they're very close to the same value. So it doesn't actually matter if you give yourself a push at the start or not. What matters in this case is the height of the slide and the change in your gravitational potential energy. That's what is influencing your final velocity here. So just first off, thought that was interesting example. Here how the initial velocity really doesn't matter. And you can kind of see that this will be the case. I should have a parentheses. With this term here, that's much bigger. This is just going to be 2 because it's 2 squared is 4 divided by 2. That's just 2. 9.8 times 36, that's pretty big. So that term is way bigger than whatever your initial velocity is going to give you. And that is all that is included in this other one. So it makes sense that they're very similar. Maybe if you were able to give yourself a really big initial velocity, it might matter, but not in this case. So that is everything for this lecture. We are going to practice this more also in class on Thursday.